Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, Assalamu alaikum. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Dear student, today the topic of our discussion is HPLC ICPMS, one of the hyphenated technique uh, in mass spectrometric and thermal method of analysis having course code CHEM453. First of all, HPLC connected to ICPMS. The HPLC ICPMS is a technique that combines the physical separation capabilities of HPLC and analysis power of a mass spectrometer. It is the method that combined separation power of HPLC, as I mentioned it, because HPLC used an analytical chemistry, a very good technique for the separation of different compounds in a mixture or different components in a mixture. And on the other hand, mass spectrometer is a very good analytical technique having a very good detection power. So, so in HPLCMS and LCMS, we remove the detector of HPLC and fit the column to the interface of a mass spectrometer. So, in most cases, the interface used in HPLC, ICPMS, or LCMS are the ionization source. So, HPLC is a method of separating complex matrix into its component. While on the other hand, mass spectrometry is having a very higher sensitivity to give the information about the identification and structural information of analyte. So, combining these two, HPLC plus ICPMS, we are getting a hyphenated or coupled technique known as HPLC ICPMS. As the analyte elute at the end of LC or HPLC, liquid chromatography, it is entering into the mass spectrometer where it is ionized, and then those ions are separated on the basis of mass to charge ratio in a mass analyzer, and finally detector in the detector system. So this is the combined system of HPLC. This is HPLC, and this is connected to a mass spectrometer, and then these whole two instruments are connected to the computer, which uh, ultimately gave us chromatogram plus mass spectrum of some specific component of a mixture. So here this is a system of HPLC having this solvent system, and then degaser, and then a column is this is a column of chromatography, and then this column is attached. This is further attached. This is a column is further attached by interface with a mass spectrometer. But the problem while combining LC with MS, that first of all, HPLC is operated at a liquid phase, and this is working at a temperature of 25 to 50 degrees Celsius. No mass limitation of HPLC, and require inorganic buffer and require a steady flow of 1 ml per minute. On the other hand, this MS is working at a vacuum operation because it is very difficult to control the ions at atmospheric pressure. So the vacuum is needed. So the air is evacuated from mass spectrometer. It is working under a very low pressure. So working at a temperature of 200, from 200 to 300 degrees Celsius. So there is a difference, means this is working at a room temperature or even slightly higher, and this one is working at a higher temperature like 200 to 300 degrees Celsius. And this is the mass limitation, specifically if you are using quadrupole mass analyzer, so 4000 Dalton, and it require organic volatile buffer can work at a flow of 10 ml per minute. So, so Uh, mobile phase is one of the key component of HPLC. It must be low cost, having high purity, low must be having a low viscosity, non-toxic and non-flammable. Also, uh, must be non-corrosive to LC system components. Column is one of the most important component of HPLC chromatography because the separation of sample component is achieved when those components pass through the column. The high performance liquid chromatography apparatus is made out of stainless steel tube with a diameter of 3 to 5 millimeter and length ranging from 10 to 30 centimeter. Normally, columns are filled with silica gel because its particle shape, surface properties, and pore structure help to get a good separation. Silica is wetted by nearly every potential mobile phase and itself is inert to most of the compound and has a high surface activity which can be modified easily with water and other agents. Silica can be used to separate a wide variety of chemical compounds and its chromatographic behavior is generally very predictable and reproducible. This is the picture of HPLC column. This is how it looked like, made of a stainless steel. Inside the stainless steel, this stationary phase is filled inside like a silica. Fast column are usually short columns ranging from 15 to 50 millimeter, while micro LC columns, long column 20 to 150 millimeter. Sample preparation is one of the key in HPLC ICPM system, concentrating the analyte while removing the material which can cause interference. Now you will see what can interference cause in ICPMS system. So pre-concentration is one of the technique used for the sample preparation, and desalting is also is one of the technique used to usually used to remove the salts like NaCl, potassium chloride, or potassiums, and filtration to remove a lower molecular weight drug from proteins, plasma, and the milk. So interface is in LC-MS system. If LC is directly connected to the MS system, the liquid phase would vaporize and resulting in larger amount gas being introduced into the MS system. So resulting and decreasing the vacuum level, which will stop the ions to reach into the detector. So uh, when LC, this HPLC is connected to ICPMS, till here, um, in one of the lecture, we have already discussed these two or three slides for HPLC system. But HPLC connected to ICPMS, we haven't discussed ICPMS system. So coming to the HPLC ICPMS system, and we will discuss in more detail the ICPMS system. Like what? We will discuss, first of all, the introduction of ICPMS system, that what is ICPMS, when HPLC through this interface is connected to the ICPMS, what is happening to the analyte in ICPMS, how does ICPMS working, and what are the different parts of instrument, for example, this instrumentation. First of all, how the sample is introduced when it is going from HPLC system to interface into the ICPMS system. So the first component is sample introduction system, and then ionization and plasma occur, and then this mass separation and ion detection. This is inside the instrumentation. And after instrumentation, the analytical procedure we will discuss, like calibration of ICPMS, interferences caused in the by different component in ICPMS, how those interferences are corrected, and then the detection limits of ICPMS, different instrument, and tuning of ICPMS, and last one, data reduction, how the data is carried out, how the data is presented, how the data is processed, and sample preparation and lab safety. And at the end, we will discuss in this ICPMS system. First of all, what is ICPMS system? What is ICPMS good for and why? This is the multi-element analysis, consists condition for most or all of the element in the periodic table. So inductively coupled plasma mass spectrometry not only offers extremely low detection limit in a subparts per trillions, means PPT range. So in this lower, it is having a very lower detection limit, means subparts of parts per trillion PPT. But not only it gives you a very low detection limit in parts per trillion, but also enables a wide dynamic range capability. This unique technique has having the capability makes the technique very attractive compared to the other trace metal technique, such as electrothermal atomization ETA, which is limited to the determination of trace level, flame atomic absorption, or inductively coupled plasma optical emission spectroscopy (ICP OES), which are traditionally used for the detection of higher concentration. So this instrument is having with wide elemental coverage, almost except hydrogen, noble gas, and fluorine. It covers all of the element present in the periodic table. Having a very detect, as I mentioned, it having a very low detection limit, also having a wide dynamic range from 10 to the power 9 to 0.5 ppt, means 500 ppm dynamic range, and short acquisition times, means full mass is scanned in less than 5 minutes. Like let's say you are scanning for analyte having a mass range from 5 AMU till 10,000 AMU. So the range is quite broad, but it takes a full acquisition less than 5 minutes, and good metrics are tolerant, even like in other mass spectrometric like ESIMS, like EIMS. If even you don't clean the sample very well in this technique, this can tolerate the metrics to a very good level. It will handle acid, solvent, metrics up to even 0.5%. So although like there are few interferences caused by different component, but very few interference. Most problematics are gas blink, molecular ion, other polyatomic species. Small number of consistent, predictable, high-intensity peak plasma species. A large number of variable list. So means a matrix is not affecting, not interfering very much. So, uh, uh, while generally discussing the instrumentation of um, ICP-MS, inductively coupled plasma, first of all, the introduction means still, I would say, this that inductively coupled plasma mass spectrometry is undoubtedly the fast-growing trace element technique available today. Since its commercialization in 1983, approximately up till now, 5,000 systems have been installed worldwide. So carrying like means many diverse application. The most common one, which represent the approximately 80% of the ICP-MS analysis being carried out today, include environmental application, geological application, semiconductor, biomedical, nuclear application field. There is no question that other major element determination at ultra trace level uh, is performed by this technique. Uh, so, coming to the principle of operation of coming to the instrumentation of ICP-HPL's ICP-MS system. In ICP-MS system, the sample is introduced into the plasma coming out of the HPLC system from the column into the plasma, and then inside this plasma, ions are basically created, and these are lenses which attract these ions to the mass analyzer, and mass filter, and then so there are a number of different designs available of ICP-MS nowadays, which share many simple components such as nebulizer and nebulizer, spray chamber, plasma torch, and detector, but can differ quite significantly in design of interface, ion focusing system, mass separation devices, and vacuum chamber. So the means the different system, the plasma system is similar, while the difference is there in the ion focusing system. Mass separation means some use quadrupole mass, some use magnetic sector mass analyzer, so etc. So, um, so the principle of operation is the sample, which usually must be in a liquid form, is pumped at 1 ml per minute, usually with a peristaltic pump, into a nebulizer, and where it is converted into a fine aerosol with argon gas at about 1 liter per minute. The fine droplet of the aerosol, which represent only 1 to 2% of the sample, are separated from larger drop by means of a spray chamber. The fine aerosol then emerges from the exit tube of the spray chamber and is transported into the plasma torch via sample uh, injector. It is important to differentiate the role of plasma torch in ICP-MS system compared to ICP-OES. The plasma is formed exactly in the same way by the interaction of intense magnetic field produced by uh, produced by radio frequency passing through a copper coil on, on a tangential flow of gas, normally argon at about 15 liter per minute flowing through concentric quartz tube. This is the effect of ionizing gas, and when seeded with a source of electron from a higher voltage spark, form a very high temperature plasma discharge around 10,000 Kelvin at the open end of the tube. However, there is a very similarity. There is there, this is where the similarity ends in comparison to ICP OES. Mm. So this is the plasma system, and this is the how ions are generated. This is the sample introduction system. Sample is introduced here, and then ions are this is the ions are generated here, and then ions are accelerated here, focusing and and translates to the mass separation device. So this is the sample introduction fluids. Sample are introduced with the nebulizer like this. First of all, the sample introduction system. Sample are introduced with the nebulizer like this, which aspirates sample like this, aspirates with a high voltage argon forming a fine mist. This aerosol, this is a nebula. This argon gas is going through here. This is pumped by a peristaltic pump actually. So this is around 100 millimeter large. So aerosol passes into a spray chamber, basically a spray chamber where a larger droplets are removed via drain. This is like this aerosol, this nebulizer is passing through a spray chamber. The larger droplet due to the gravitational force are drained here. So only 2% of this original mist enter into the spray chamber. So processes yield droplet small enough to be vaporized in the plasma torch. In the plasma torch. So sample introduction alternative like solids. Alternative sample introduction is the laser emulsion. Means not all of the samples are in liquid form. Means of course, more than 90% of the sample is in liquid form. But what about the 10%? So for the solid sample introduction system, this laser emulsions having the resolution between 25 to 300 micrometer depth profiling to this one. Uh, this is having some application in trace element and mineral growth zone and shell forensic and archaeological fingerprinting. But most of this sample is in a liquid form. So this argon plasma basically generate ions, as I told you that how argon plasma is generating the ions. This argon plasma. Uh, Discussing these, uh, we are coming to the sample flow. That sample is flowing through, and it is these are the quartz tube. These are the magnetic field radio. What I told you. So the argon gas is flowing through it. Um, so discussing the ion formation in inductively coupled plasma, how argon plasma generate ions. In inductively coupled plasma mass spectrometer, the sample, which is usually in a liquid form, the sample is pumped into the sample introduction system, comprising a spray chamber, uh, comprising a spray chamber and nebulizer. Is in a previous slide, I, I, I showed you that this nebulizer. It emerges as an aerosol, where it is eventually find its way via sample injector into the base of the plasma. From this one into the plasma, uh, as it travel to the different heating zone of the plasma torch. Uh, these are the different heating zone of a plasma torch. As it travels through the different heating zone of the plasma torch, it is dried. This sample is dried uh, and vaporized, atomized, and ionized. So as it traveled through the different temperature zone like this, coming from this to tell like the maximum temperature of the plasma is around 10,000 Kelvin. So it is dried, vaporized, atomized, and ionized. During this time, the sample is transformed from liquid aerosol to a solid particles, then into a gas. When it finally arrives at the analytical zone of the plasma, around 6,000 to 7,000, this is the analytical zone, 6,000 to 7 Kelvin, it exists as a ground state atoms and ions. So means if you are subjecting the molecule into the plasma, like for example, carboxylic acid, for example, any first of all, it is broken into the element, and then element into the ground state atoms. And then they are ejecting the electron out of it, and ions representing the elemental composition of the sample. The excitation of the outer electron of a ground state atom produce a wavelength specific photons of light is the fundamental basis of atomic emission. However, there is also enough energy in the plasma to remove electron from its orbital to generate a free ions. The energy available in the energy available in argon plasma is around 15.8 electron volt, which is extremely high, which is high enough to ionize most of the element in the periodic table. The majority of the element in the periodic table have the have this majority of the element, this is ionization potential. This is having atomic number from 0 to 100, let's say, different element like arsenic, like selenium, like chlorine, etc. All these elements, like except few element, you can say fluorine, argon is here in neon. So the ionization potential of all the element is below the maximum ionization, the maximum energy of plasma having 15 electron volt. So it can ionize, you can say, the entire periodic table except few these elements. So majority of these elements is ionized, having ionization potential in the order of 4 to 12 electron volt. It is the generation, transportation, and detection of significant number of positively charged ions that give ICPMS its characteristic ultra trace detection limit capability. It is also important to mention that although ICPMS is predominantly used for the detection of positive ion, negative ions are also produced in the plasma. However, because of the extraction and transportation of negative ions are different from that of very simplistic view of chromium 0, consisting of nucleus with 24 proton, chromium and 24 proton and 28 neutron, and surrounded by 24 orbiting electron. It must be emphasized that this is not meant to be an accurate representation of electron shells and subshell, but just conceptual explanation for the purpose of clarity. Uh, um, from this, we can say that the atomic number of chromium is 24, 24 number of proton. Its atomic mass is 52 number of proton plus neutron. If energy is then applied to the chromium ground state atom in the form of heat from a plasma discharge, one of the orbiting electron will be stripped off of the outer shell. This will result in only 23 electrons left orbiting the nucleus. Because the atom has lost a negative charge but still has 24 proton in the nucleus, it is converted into an ion with a net positive charge plus 1. It still has an atomic mass of 52, atomic number of 24, but is now positively charged ion, not a neutral ground state atom. So this is how ions are produced in the plasma and how this is working. So then once the ions are created in the plasma, then these ions are extracted by ion extraction interface. Once the ions are produced in the plasma, they are directed into the mass spectrometer where the interface region, which is maintained at a vacuum of 1 to 2 tau with a mechanical rough pumping. This interface region consists of two metallic cone, um, usually nickel, called the sampler cone. This is a sampler cone, and a skimmer cone, each with a small orifice, small hole of zero point 0.6 to 1.2 millimeter to allow the ions to pass to the ion optics, where they are guided into the mass spectrometer device. The interface region is one of the most critical area of ICP mass spectrometer because the ions must be transported efficiently and with electrical integrity from the plasma, which is atmospheric pressure at a 762, to the mass spectrometer analyzer region at approximately 10 raised to the power minus 6 to. Unfortunately, there is a capacitive coupling between the RF coil and the plasma, producing a potential difference of a few hundred volt. If this were not eliminated, it would have resulted in electrical discharge called a secondary discharge or pinch effect between the plasma and the sampler cone. This discharge increased the formation of interfering species and also dramatically affect the kinetic energy of the ions entering into the mass spectrometer, making optimization of the ions optic very erratic and unpredictable. For this reason, it is absolutely critical that the secondary charge is eliminated by grounding the RF coil. There have been a number of different approaches used over the in previous years to achieve this, including a ground strip between the coil and interface, balancing the oscillator inside the RF generator's circuitry. A grounded shield or plate between the coils and the plasma torch are use of double interlake coils where RF fields go in opposite direction. They all work differently, but basically to achieve the similar purpose, the similar result, which is to reduce or eliminate the secondary discharge. So, dear student, this is enough for today. On our next lecture, we will discuss some more detail about the ICPMS.